Can you close the door, please? Is everything fine? Can you close the door, please? Hello, everyone. So welcome to this lecture on memory-centric computing. I'm Geraldo. I'm a senior PhD student here with Professor Onur Mutlu, and I'm doing my PhD thesis on this topic. So we are going to talk about a lot of my works and also works that our group have been doing in this field, and also we are going to touch some of what industry is doing because this is getting a lot of popularity these days. Before I start, I believe that you can go to the website for this seminar class, and over there you're going to see the distribution of papers and the dates. If I'm not mistaken, I think it should be already there. And over there, you're going to have the names of the two mentors that you're supposed to work with. So please go ahead and send your message to the mentor, send an email to the mentor, so you can schedule the discussion presentation. So you're going to have like one meeting for discussing your slides and another meeting for a dry run. So do that as soon as possible. Particularly for the dates that are around the end of November, because we have some conference deadlines over there, and your mentor might not be as responsive as if you send the email now. So don't wait so much for scheduling that meeting. And you recall that you need to schedule 2 meetings. So there is also, you don't want to do all of the 2 meetings in the week of your presentation. So do them as soon as possible. And if your mentor does not reply to your mail, just send another one. And if they don't reply, send another one and another one, because we are really bad at replying mails, but we are getting better. You have a question? Sorry? Send the email to both. The same email, CC both, and you can see the emails of everyone in the website as well. So just send a single email to both of the mentors together. Any other question? Okay, so let's get started. We have a lot of slides to cover. Okay, what is the question? The person didn't write down the question. Okay, you can ask your question over Zoom. I think we should be connected here in the room, or you can write down in the chat, and Ismail is going to read it. Okay, if that person write down the question, let me know. Okay, so let's get started. I'm going to talk about a lot of our works over here. So this is more an overview lecture than deep down in anything that we are working. Is more for you to be familiar with the topic and the works that are going on currently and in the past. So yeah, so let's get started. So the main problem that we're trying to solve over here with this memory-centric computing paradigm is that computation today in your system is bottlenecked by data. And this comes for many different reasons. The first one, for example, is that many important workloads, for example, I'm going to talk a little bit later about ChatGPT or large language models, right? They are getting a lot of popularity, and their popularity is because of their data-intensive behavior, or they are as good as they are right now because they are trained over a lot of data. And that exacerbates not only the computation, but the memory requirements of the system. They also require rapid and efficient processing of large amounts of data. So for example, even though you do training over a large amount of data for the large language models, you are going to do inference as well over some really large model parameters. And that is going to exacerbate this memory bottleneck problem. And as I'm going to show later as well, data is increasing. So last year, OpenAI released ChatGPT with some model. They had some million of parameters, and they already foreseen ChatGPT GPT-4 which already growed a lot in a really short period of time. So this is an example of what I'm talking about, this machine learning user case. So here you can see the memory requirements for different models and the training, the compute throughput that you requires. And in the first release of BERT, this is the model from Google in 2018. That model was requiring around 1 gigabyte of data. And now in ChatGPT, 2 years later, you required almost 4 times the order of magnitudes larger amount of data. So that was increasing the data requirement for these large language models in less than 2 years, which is a quite explosive amount of data. And this is not the case only for neural networks. If you look at databases, graph processing, memory analytics, and data centers, this problem of data movement bottleneck is all over there. So, and creating both performance problems and energy problems for those systems. So I'm going to talk about this work a little bit later. And this is just to highlight that the problem is not only on the cloud or on your desktop computer, as your mobile system is quite powerful nowadays, and it also processes a lot of data-intensive tasks like Google Chrome or some neural engine local in your edge device, or when you go to YouTube, you need to decode and encode some videos, and all of this creates data movement and performance and energy bottlenecks in your system. In other domains like bioinformatics, this also happens. So this was exacerbated in the 2 years ago with the COVID pandemic, because we need to sequence the information of that virus quite quickly, right? And that requires a lot of data as well. And when you do tests with human genomes, that also exacerbates this data movement and data bottleneck problem. And this happens because the data movement in the systems happens only on the processor. So you have in the system your processor, your computation, but you also have a lot of communication, a lot of data moving from this processor from the storage and memory to this processor, and this impacts several metrics of the system. And just to give an overview on this the way that we design systems has been initially proposed or has been initially studied for many years. So this is a seminar paper from von Neumann, and you're going to hear a lot of, or when you read these papers for the seminar class, you're going to be hearing or reading about this von Neumann architecture. And this von Neumann architecture is the architecture that, even though it was proposed in the 40s, is what we still have today, where we divide the components of the system into 3 main components: computation, communication, and storage or memory. So this is what originally von Neumann proposed. And now this memory storage unit is splitted and getting deeper and deeper, because now the memory system and the storage system have many levels. And if you look at what we have today, so this is what von Neumann proposing in the 40s. And what you have today is pretty much the same. So the red here is this is a picture of a die of a processor. So we have several cores here in red, and everything in green over here is just dedicated to either store memory or to store data or to move data. So the majority of the system is actually dedicated only to data movement or data storage itself, and computation becomes a small portion of the system. And there are many different solutions to alleviate this data movement bottleneck problem. And the classic solution that memory or processors manufacturers like Intel or AMD have been taken over the years, and still take today, is to basically extend the cache hierarchy of your processor. Or either extending in numbers of levels. So nowadays it's common to have at least a L3 cache, so 3 levels of caches in your system. Some systems also include a 4th level of cache, L4 cache over here. And then you keep increasing the size of the last level cache in every single processor generation in the hope to alleviate this data movement bottleneck problem. So this is an example of a die from 2020 from IMD. And if you look at another die from 2021, so in the previous die here, L3 cache was 32 megabytes. And then in the next generation, it's not necessarily exactly the next generation, but 1 year later, this was increased to 96 megabytes of L3 cache. And this continues to other processors. Those are AMDs. I think this one is IBM, yes. So yeah, so you have a huge L3 cache of 120. And if you look at the Apple M1 chip over here, you can see that a lot of the space of the die is also dedicated to this deep cache hierarchy. And even though this is an okay solution and has been shown to work for many years, nowadays, because of the properties of the applications and how the applications are being developed, and this cache increasing is not enough anymore. So we did this study with Google workloads for edge devices, and we saw that even though that particular system has some quite deep cache hierarchy, still many of the workloads that was running over there was creating this data movement problem. So over here, almost around 60% of the total energy of the system was spent only moving data. And if you look at accelerators, so this is for edge TPU accelerators for neural network inference in Google, the same problem happens. More than 90% of the total system was spent on moving data across this accelerator. So the problem that you have then is that data is creating this performance and energy bottleneck in the system. And this comes from the way that we design systems. So this RowHammer architecture where we divide computation from storage from communication. And this creates energy waste and also create performance loss. And the entire problem is that we are not performing computation where the data resides. So we are always having to move the data from your storage device, from the DRAM, from the caches into the processors, so that you can do some particular computation, even though the computation might be really small. And so this creates the entire problem. So you might think that this is a new problem, or is a problem that was is created because of the way that we are using the systems today. But actually that was already foreseen many years ago. So there is this seminar paper from Richard Seitz from 1996 that's called "Is the Memory Stupid?" And this is the title of his paper. I'm not calling anyone stupid. And over there, he already foreseen that at some point in time, the memory subsystem is going to become the only important design issue for microprocessors, because the rates where a processor speed was increasing and the rate where latency was increasing for storage or for DRAM or for caches was not in the same pace. So one was increasing much faster than the other. So the speed of the processor was the processor speeds after one generation after generation was increasing much faster than the memory speeds. And then years later, so this is from 1996, years later, this is from Professor Onur Mutlu's PhD thesis in 2003. He did some studies with some important workloads from Intel at the time. And then you can see that this is execution time across all of those workloads, that more than 50% of the execution time for those workloads was already expanded in the L2 misses, in the cache in the system itself, instead of being spent doing useful computation. And yeah, so this is, and then he, in his PhD thesis, he's tried to alleviate this with this run-ahead execution. But later on, this is another study from Google from 2015 for their server workloads. They observed the same thing. So this was from 2003. And then later on in 2015, again, for this important workload from Google here, a lot of time in the execution of those applications were spent moving data instead of actually computing. So the green thing here is the time spent in computing, and you can see that it's really small compared to the time of moving the data. Again, this is for the same analysis for those workloads. You can see around at most 70% of the time, around 50% on average of the cycles is spent just moving data. And why, again, this data movement problem is being generated is because we are designing really imbalancing systems. Again, it's really important to emphasize that the processor here is the only way of doing computation in your system. So anytime that you want to do something, you need to move the data from that memory subsystem into the processor, and which creates an imbalance in the way that the overall system is designed. And then there's a lot of elements in the processor itself right now designed just to try to tolerate this data movement bottleneck. So I talk a lot about over here about the cache hierarchy, but which is a way of alleviating this data movement bottleneck, keeping this processor-centric system. But also there are many other things in the processor. There are prefetchers that are trying to predict what is going to be the next address that you're going to access for that particular application. And this is another mechanism to alleviate data movement, to try to alleviate data movement. There is also speculative execution that out of these processors are aggressively implementing, trying to also alleviate this data movement bottleneck. But this just adds extra cost and not extra complexity on top of the processor design itself, instead of fundamentally solving the problem. From the energy perspective, so I'm talking a lot about performance, but this data movement creates a lot of energy problems as well. The overall problem here is that if you want to do a complex operation in your system, like a double precision arithmetic operation, you take around 20 picojoule to do that computation. But if you want to access the memory, you're going to take 16 nanojoule to access some data stored in DRAM. So this is around 2 to 3 orders of magnitude larger energy to move data in comparison to actually do computation. So this is another view of the same graph over there. So here you can see that when you are moving into the memory hierarchy, so going from the register file to the caches to the DRAM, your energy increases significantly every time that you move deeper and deeper into the memory hierarchy, leading to, in this case, and this is a particular example here, around 6,400 times larger energy when you go to the last level of the memory hierarchy instead of doing computation locally in the processor. So this creates a lot of problem, and the way to solve this fundamentally is to think about a paradigm shift. So instead of thinking about the processor as the only way of doing computation or the only place in your system to do computation, we need to think of ways of enabling computation without data movement, or with the minimal data movement possible in that particular system. And the overall mindset here is to do computation where the data resides. So if you do if your data is in your DRAM, for example, there is no reason for you to move it in the processor, or if it's in the cache, why moving into the registers in the processor to do computation? And this is what we call the data-centric architectures, because we are going to think not about the computation, instead of we're going to think about where the data is, and later on think about the computation. So an intelligent architecture that is well designed should handle well these data movement problems. And what we want, what do you mean by this handling data well? So we want to ensure that the data does not overwhelm the processor or the processing units that you have in the system. And this can be done by several ways. It's not just by moving the computation, but also by designing new algorithms that takes the data movement into consideration, new architectures, and also co-designing the entire system to have that into this data movement into account. We also can think about way of using the data that is going through the system to design better processors themselves. So if you look at your processor design, and in several papers that you're going to read, you're going to see that a lot of parameters that are in the size that are in the system. For example, how many levels of the cache hierarchy should I have? 3, 4, 5, or how many? What should be the set size of your caches, or what should be the size of how should your prefetchers be configured. So all of those parameters are often set in the processor design time only based on local decisions. So without considering which algorithms are going to run or properties of the algorithms that are going to run over there. So we can also improve the architecture design by taking into consideration which type of data that particular design is going to use and how that particular data is going to be used. And finally, another way of handling data well is to understand and exploit the different types of data that you have in the system to improve algorithms and improve architectures overall. So the computer system that you have today, just to sum up this part, are what we call processor-centric, because the processor is the center of everything. Everything needs to be coordinated by the processor, and we don't necessarily want that because this creates this data movement problems that we were talking about. Instead, we would prefer a data-centric architecture where by doing the computation where the data is, we would eliminate the problems with performance and energy. And we want to make decisions on the system design based on the data that is going around that system instead of being ad hoc decision dictated by the designer doing the implementation of the processor. And we want to do data-aware decisions as well, instead of doing decisions only based on a small view or particular element of your system. So overall, we want a data-centric architecture, we want a data-driven architecture, and we want a data-aware architecture. And yeah, there is this of what I'm going to talk about. You can read more in this paper that we published some years ago. But overall, for us to be able to do that, to have a more memory-centric architecture, we need to rethink the entire system stack, because now we are going to be able, and then you're going to see this why later on as I advance in the system, but basically we need to rethink overall algorithms, and we need to rethink the interface between algorithms and the hardware themselves. So let's get started with the overall the design of this data-centric architectures. Is there any questions so far? Feel free to stop me at any point. So I guess not. So this is the properties that we want for this data-centric architecture. So the first thing, the most important thing, is that we want to process data where the data resides. So we want to do the bare minimum data movement possible in the system, so we don't create performance or energy problems. So we want the memory to be low latency and low energy as much as possible, and this involves usually doing the computation nearby the memory itself. And we also want to have low cost of data storage and processing, because we want also a system to have high memory capacity, because there is a trade-off between energy, performance, latency, and capacity in the system. And you want to intelligently manage the data into the system. And this involves designing intelligent controllers, making decisions, intelligent decisions about security, cost, and performance of the system. So let's get started then with the processing the data where it makes sense. So again, I have this picture here from the Apple M1 processor die. And as you can see in this picture, the majority of the system is just dedicated to storing the data itself. So if you have the majority of your die just dedicated to store the data, the place that would make sense the most to do the computation is where most of your die is, right? So why I would only have a small portion of your die dedicated to processing, and all of the rest just auxiliary steps to do this computation instead. So we need to think differently from this different approach. So this is an overall picture of what we want. So so here we have your system, we have your CPU cores, and you have GPU cores on some accelerators, the cache hierarchy, the memory controller, your main memory device, and then we want to equip the memory device itself with some key computing capabilities to enable performing computations for a large set of operations. or applications. So this is very similar to conventional accelerator systems, but as we're going to see next, just by moving some computation to inside this memory, this involves a lot of rethinking on how the architecture step should be designed. So this idea of memory-centric computing, again, is not a new idea, and it's kind of actually really old. So the first paper that talks about this logic in memory type of design is from '69, and then there were several other papers in the '70s about it, and then in the late '90s there was so that trend died a little bit because processors became faster and faster, and then this trend came back again in the late '90s with the intelligent RAM project. And then it died a little bit with the multi-core era in the early 2000s. And nowadays, again, it's kind of trying to talk about this memory-centric computing. So why memory-centric computing is important today, and we should care about this today, and not necessarily it made it in the '70s or in the late 90s, and this is related to how we are dealing with systems today. So we have this huge problem with the scaling of the memory technologies themselves. I'm going to talk a little bit later on that. We have a huge demand from the applications, and in the end, you have us designers sitting in the middle. So related to these problems with the memory technology themselves, so as probably you are familiar with these effects, every time that you have another memory generation, we have a new generation of memory devices or storage devices, and the size of the transistors keep decreasing and decreasing, so you can increase the capacity and the density of your memory device themselves. And now we reach to a point where the cells and that transistor size is so small that it creates scaling problems, and scaling problems that involves, for example, security implications of the system itself. There is this huge demand from applications. A lot of these memory-centric, especially the industrial portions of memory-centric computing, is driven by the demand from key applications like recommendation systems, bioinformatics, or nowadays these large language models, which exacerbates these data movement problems, and overall there is this need to improve a system, not only on terms of performance, but also in terms of energy and in terms of sustainability. And when you try to combine all of the three, I would also add a fourth-year course. When you try to add everything to a single system, is pretty hard to do so with the processor-centric design. So also because of this. Of these demands or this technology advantage that we have over time, industry itself has given a push into this memory-centric computing type of architecture with different technologies. So one of these technologies that reignites this research in memory-centric computing in 2012-ish and 2013 is this 3D stack memory technologies, where you take several memory dies and then you stack them together in a single package using 3 silicon vias, what's called. And one of the first example of these designs was what was called this hybrid memory cube memory. Nowadays it's not available anymore, was discontinued, but it's quite common for you to see around this hybrid bandwidth memory, HBM memory in your if you have a GPU graphic cards, is what they often use, and is the same idea of stacking several dies together to allow high bandwidth, and then there are many pushes from the memory manufacturer. So Micro around the same time released this autonomous processing engine, and I'm going to talk a little bit later about this UpMem architecture from this French startup. Samsung is pushing a lot in this direction as well, with several different memory technologies. Also SK Hynix, again Samsung, Alibaba, as well. So yeah, so there are many other chips from other startups pushing this direction. So yeah, and just a brief detour from this memory-centric. It's not necessarily a detour, but one thing that none of those memories can solve by itself is this scaling problem. So the memory gets smaller and smaller and smaller, and because of that, it can create some particular funny or particular interesting effects in the system itself. So, and one of them is the fact that you can induce errors in memory chip devices by the way that you access the data itself, and this is what is called the RowHammer effect. So this is all related to the scaling problem. So again, remember the cells get smaller and smaller over time, and then you try to pack many cells together in the same DRAM array. So this is a graphic view of a DRAM array itself. So you have many rows connected through what's called word lines. And the way that this works is basically you activate or you access one of those word lines. So you open the row and then you read the data from that row. And then when you're done reading the data, you close that row by sending what's called a precharge command. And because of this scaling problem, some research have shown that if you keep doing this, if you keep open and closing the row, a single row, at some point you see bit errors in some adjacent rows to that one that you are accessing. So you are not necessarily activating or open the nearby rows. You're just activating and open one row over here. And by doing so, you are creating bit flips in nearby locations of that particular row. And this is quite consistent across different DRAM devices from different memory manufacturers. So this is a study for 2014 that we did over here, and by doing so, you can create security vulnerabilities in your system. So you can actually, with this hardware failure over here, you can gain access to a particular device by doing this RowHammer effect. So this was shown first in this paper in 2014, and it is still going on nowadays. So you're still conducting research in this field because years later on, you're still having the same scalability problems actually becoming worse over time. So yeah, so there are a bunch of talks on this particular topic and how we discovered this in your group, and overall, one way of solving this problem is designing intelligent controllers, so we can mitigate this, or we can avoid giving attacker particular control of your system to exploit this RowHammer vulnerability. And then we have some examples of such intelligent controllers in your system, in the research of your group with this BlockHammer paper, and also memory manufacturers are looking into those and how to mitigate this RowHammer security problem. So this is SK Hynix is one of the main memory manufacturers that you have today. The three biggest ones are Samsung, SK Hynix, and Micron. And yes, so they are publishing papers and looking at solutions. So this is for example, a picture of a DRAM die over here. So we have these arrays. They are organized into groups, and they put some counters over there to try to mitigate this RowHammer vulnerability in the system. And yeah, so other memory manufacturers also are looking into solutions to that. So this is the Samsung case, and so the first time that this was shown was 2014. Then you can ask like, okay, Samsung, SK Hynix, and memory manufacturers are looking into this and are trying to solve this problem. So are we done? Is this RowHammer problem mitigated? But it's actually not true. So in 2023, we show yet another way of creating what's called these read disturbance errors in DRAM chips with this rope as another type of vulnerability that can be exploited by attacker to gain control of your system. And this was just shown this year in this International Symposium of Computer Architecture venue from our group. And also other memory technologies requires intelligent controllers so that we can mitigate the scalability problems. So this is yet another type of memory technology. So one way so since we are having all of these scalability problems with main memory, with DRAM, and creating the security breaches with RowPress and RowHammer, we can think of, okay, maybe we should just replace DRAM with other memory technologies like phase change memory. And there have been several proposals for many years to try to find yet another memory technology that can replace DRAM so that we can mitigate these scalability issues. But it's quite a hard problem because DRAM gives you a really good trade-off point in terms of cost, speeds, bandwidth, and capacity or density of the chip itself, which those other memory technologies fail to give in at least one of those metrics. So yeah, so industry is trying to mitigate this problem, is looking into these scalability issues as well. This is a paper that Samsung and Intel wrote together about these problems of scalability of DRAM. And again, another work from Samsung. And the overall takeaway here is that by designing intelligent memory controllers, or you can avoid or mitigate some of those issues and enable better scaling of the memory device. But this is just a remedy. This does not necessarily fundamentally solve the memory bottleneck that you still have in the system, because even though you can create some way of intelligently deal with your memory device and deal with that limitation to that particular device, fundamentally, you are still bottlenecked by the data access in terms of both energy and performance. So in order to design better systems and have high performance and energy efficiency and sustainability all of the same time, we need to think about this memory architecture, memory-centric architectures for several applications, key applications in this system. And overall, what we want is not much different that is already here. So basically, we want a way to tell my memory device, we have that data stored there in your DRAM array. Please add this data together, or do a multiplication together of this data and give me the outputs instead of moving all of the operands to the processor to do that operation itself. So if you want to do that, there are many questions. So which computation should we give to the memory device? Because we also don't want to just take a processor, the entire processor, and move to the memory, because again, memory is a really cost-sensitive technology. So putting an entire processor into the memory device would create a lot of costs and a lot of thermal issues, which we don't want out of the blue to put a heat sink on top of your DRAM device. So what type of computation should we put over there? What type of processors and communication units should we add on top of that? How does the software and hardware interface looks like? How does the system compilers and operating systems and programming language should look like to enable this? How should we redesign algorithms and the technology of the cell itself, of the transistor itself, to enable this type of computation? So overall, this spans the entire enabling this type of computation spans the entire system stack. And what I'm going to talk over here next is there are a lot of information that I'm going to talk. You can read more on this book chapter that we have called A Modern Primer on Processing Memory. It's quite a long book chapter, and a lot of the material is over there. So if you're curious about processing memory, I highly recommend you giving it a look. So let's get started in the architectures of processing in memory. Before that, is there any question? Okay, great. And we are going to talk about two different ways of doing processing memory. The first one is processing processing use is the other way around. Is the processing using memory. So you're not going to add any logic to your memory array itself. I'm just going to changing the way that the memory operates, I'm going to enable some simple computations in the memory device itself. And then the other way of thinking about processing memory is by this process or process near memory architecture solutions, where we are going to move the computation logic closer and closer and closer to the memory array itself. So this is two different ways of thinking about processing memory. So first, we are going to start with the process near memory solutions. And this is where industry is leading to nowadays. Later on in these slides, I'm going to show some examples from some really recent examples from industry. So this is we start looking to this process near memory architectures in our group around 2015. And one of the main applications that was driving the necessity of doing these memory-centric architectures back then was graph processing. So when you do graph processing, you need to use a lot of data. You need to compute on top of a lot of data, and often the computation that you perform on top of the graph is really small. So this is an example of large graphs that were everywhere and still are back then from Wikipedia, Facebook, Twitter, which is X these days, and Instagram. All of them really have computation based on graph processing. And just by increasing the number of computing you have in the system for graph processing, give you really subpar performance. So when you go for 32 cores to 128 cores, even though you are increasing the computation here, you only get 40% speed up. And this is because of this particular algorithms are bottlenecked by memory access itself. It's not because of computation. So here is an example of a graph processing kernel that is quite popular. It's called PageRank. Is the algorithm that Google was using many years to rank pages in its search. And the way that it goes, it basically traverses the graph and then assign a rank to each edge of the graph that you are processing. So the computation itself is really lightweight. So you basically have a multiplication and addition, but for you to do this over a large amount of graphs, a large amount of edges and nodes, we are going to have to access many of those edges, and this creates this random memory access problem that exacerbates this data movement bottleneck for these graph processing algorithms. And together with that, again, as I mentioned before, there was this push from this new technology around 2013 with these 3D stack memory architectures that allowed you to implement these processing near memory solutions quite easily in your system, not necessarily easily, but with low cost. Because in these 3D stack memory architectures, you stack the memory devices together, again using these vertical connections here, and and for you to put everything together, we use this base die, or what was also in HMC nomenclature is called logic layer, which is manufactured using the same technology that you manufacture your processor, so CMOS manufacturer. So basically, you have two manufacturing technologies, you having its own process. So DRAM is one process and logic is another process. And this process, if you try to put them together, they create they create problems for each other. And by doing this with this 3D stacking, I'm going to give a break. I'm just going to finish up this. With these 3 silicon vias over here, we can manufacture them in their own process, and then later on stack them together. And by using these 3D stack memories and this logic layer over here, we designed this graph processing engine inside the memory device itself called Tesseract, which basically is really lightweight cores, and all the cores connected in a network topology. And we designed the software stack and the programming abstraction of this from scratch to enable efficient data processing and data fetching of those graphs inside this near memory architecture solution. And if you compare the bandwidth that we get from this proposed system here with more conventional processor centric, we get way more bandwidth. So this gives us 8 terabytes per second, while if you just use DDR, conventional DDR4 system, you get 100 gigabytes per second bandwidth. And by doing so, by using this Tesseract architecture, we can heavily improve performance for these graph processing algorithms while reducing the energy of computing by 8 times. So yeah, this is the Tesseract paper. And before moving to other processing near memory solutions, I'm going to stop for a 15 minutes break, if that's fine. Okay, let's get started. Or is there a question?
There's a question. If you have to choose one, is data movement an important problem or a significant problem?
Is data movement an important problem or a significant problem? I would say that it's a significant problem. And I'm not going to say that it's not an important problem. But I'm not now going to not choose the other one. Anyway, it's really important and significant. But anyway, so let's get started with this significant problem and of processing memory or memory-centric computing. So before the break, I was talking about this case of including some logic nearby a 3D, inside the 3D stack memory to accelerate graph processing. And this is another example of now it's not for graph processing, it's for bioinformatics workloads, and it's not inside the DRAM, it's inside the storage, so inside the flash device. So when you do, like in this case here, is sequence analysis of your genome, for example. The way that this is done in today's systems, you need to store in your storage device the genome information that you're going to do. So you're going to align the target genome with. So, for example, this can be the genome of the COVID virus or of a human genome, and usually this takes a lot of space, and then you need to move all of that to the computing elements, right? And this creates computation overhead because of this data movement problem, and also data movement overhead, because if main memory is slow and creates a lot of energy problems, storage is even worse. So the farther away if you are from the processor, the worse that processing memory is, the worse that data movement problem becomes. Computing systems or a bunch of prior works have proposed ways of doing computation inside the main memory for sequence alignments using heuristics or accelerators, or using this type of pre-computing that's called filtering, and this reduces the computational overhead, but still you still have the same data movement overhead, because the reference genome is stored in the storage device. So the key idea here is to move that first filtering step to the storage device. So hopefully we can reduce the amount of data that we're going to move from the storage to the computing elements. So with that, we can filter, we don't need to, we filter the reference genome to only few reads, and then you only move those few reads into the computing element itself. And we can filter the reads, those ones that there are several types of reads. So here we can filter the exactly matching ones and also non-matching reads. This is particular for this particular workload. But overall, the key idea here, or the main dish here, is that by doing this filtering in the storage itself, before moving the data to the computing units, you can save in processing time, and also you can save in this data movement overhead bottleneck. And this system that you propose that does this in storage computing for this filtering is called GenStore, and by doing so we can significantly improve performance and reduce energy at a low cost. And this is the paper. Another example of this processing memory solutions, processing near memory solutions, is to accelerate applications in consumer devices, so in your laptop or in the phone or a tablet. And this is some work that we did for key applications for consumer devices at Google. The problem over here is that consumer devices are quite power constrained, and this data movement problem is creating a problem for consumer devices themselves. And in this particular case here, we analyze several applications that was running in the consumer device, like Chrome, also some machine learning inference tasks, and also some video playback and video capturing tasks from YouTube or from Hangout, for example. And then we did some analysis, and then we saw that 62% of this total system energy for these consumer devices was spent on moving data. And this is really problematic because, again, these devices are quite they have a really limited power budget. The second observation that we make is that these applications themselves, they are dominated by simple, the data movement that those applications are creating is dominated by simple functions or simple instructions. And then we can move those simple functions or instructions to the memory device using small embedded low power cores or some fixed function unit accelerators. And by doing so, by moving these computations to the memory device, we can have large performance and energy savings for consumer devices themselves. So this is the example here from another application for the TensorFlow inference application running on the consumer device. Again, we saw a similar problem that around 60% of the inference energy was created by data movement, and this particular data movement was created by this packing, unpacking, quantization function. So we moved that pack, unpacking, and quantization functions to inside the 3D stack memory of a memory device, and we reduce energy consumption by around 50%. And at the same time, we improve the execution time of those workloads. And this is the paper that we did together with Google, and this extends to other systems and other environments as well. So there are examples of processing their memory architectures using GPU systems, and also using other applications like traversing liquid data instructions, and by accelerating accelerators for cache misses, run-ahead execution, climate modeling, approximating string matching, more bioinformatic workloads. Time series analysis is also another example of a data movement application, and this extends graph processing, graph pattern mining, databases, hybrid transaction analytical processing databases, more neural network inference, which I'm briefly going to talk about. So over here, again, we are looking at one accelerator, and this accelerator is the Google Edge TPU accelerator that for edge devices that runs different machine learning workloads. So it runs recurrent neural networks for speech recognitions, convolution neural networks for face detection, long short-term memories networks for language translation, and recurrent convolution neural networks for image caption. So all of those workloads running this small edge TPU device, and we did some analysis, and we saw these applications are again quite memory intensive, and we saw that the characteristics, the memory intensity of these particular workloads varies across the different models and within the single model itself. So we need to have some heterogeneity to support different models with different properties, and also the different layers of a single model with different properties. And we come up, so this is the baseline system. We have one monolithic edge CPU accelerator that accelerates that is used for different models and different layers. And our proposal here is to decouple and to have different accelerators. Each one of them is specialized for a particular characteristics of a given layer, and then doing the execution mapping the layer to the given accelerator, then overall improving performance, energy, and utilization. when you try to decide how many accelerators you need to design for those 24 neural network models, we see that we can characterize the layers themselves into two main classes: the classes that are more compute bound and classes that are more data centric or memory bound layers. And then we design 3 different accelerators for those 2 different classes in this paper, which in the end cost less area than designing a single accelerator for all of the layers, because the single accelerator needs to over provision the hardware resources for any given layer itself. And by doing so, we can reduce energy consumption by 3 times compared to the baseline HTPU accelerator, while improving inference throughput by 3.1 times. And this is the work that we did together with Google in 2021. And there are other examples with using simple instructions to accelerate larger kernels, doing FPGA-based acceleration of data-intensive applications. So overall, I guess what I want to mention with all of those works is that there is different solutions or different alternatives for processing near memory architectures for different applications in different types of hardware devices themselves. So FPGAs, neural network accelerators, GPUs, and storage, for example, was the example that I mentioned here. So now I'm going to talk about real processing memory architectures. So the one that I just mentioned are usually done in academic settings and are performed in simulation. So not necessarily, they are not manufactured or prototyped. But the ones that I'm going to mention next are actually devices that we can go in the market and buy them, and they implement processing near memory features. Starting with the UpMem processing memory engine from a French company. I guess they are located in Grenoble, and they proposed this system in 2019. So basically what they have over here is that they have regular DRAM DIMMs. So this is when you buy a DRAM chip, they come in this formats with several DRAM chips together. And what they're doing over here is that together with the DRAM chip, they put some processor inside the DIMM itself. So here's an example of the UpMem system. And then your memory device also can do some computation. So this is again a different view of the DIMM. So it looks exactly like the DIMM that you would buy for your regular DRAM, but it comes with some simple cores to do computation over there. This is an example of the system that they provide. So you have your regular CPUs over here that does computation. You have your regular DRAM that store data for the CPU, and you have this pin-enabled memory that is these DIMMs that have these pin chips inside them for computation. This is an overall picture, is a representation of how the pin cores themselves are, or how do they look. So this is inside that this black box over here. And over there we have some DRAM array to store the data, and then you have some simple in-order pipeline and some SRAM based memory that is used to do computation in a highly parallel way. And so we took this system, this UpMem system, against a real product. You can go and buy them. And then we went and we analyzed it to see how good it is for general purpose applications. And then we took several applications for different domains. And then this particular chip has its own programming interface, and which is quite similar to CUDA if you're familiar with GPU programming. So you took several applications, you're implementing this programming interface. We went and running the real chip, and then we create this benchmark suite called Prim to evaluate this type of architecture over here. And then we keep studying this system and what was its capability. So here, these applications are quite generic. So I don't know, they have simple things like vector addition, and have several applications from different domains like image processing or bioinformatics. And we went further and see what was the benefits of this particular system for target applications like machine learning, for example. And one of the problems of this particular processing memory architecture from this French company is that the cores that does computation inside the memory are quite simple. So they cannot do complex things like float point computation. And as you know, machine learning training, you might know machine learning training heavily rely on float points for is computing. So we went there and then we studied the effects of different data representations, different ways of implement complex functions that are used for machine learning training, like sigmoid activation function, sigmoid function. And then we've also proposed some optimizations in the software side for those particular ML algorithms for this target UpMem system. And we saw some performance benefits compared to a CPU and a GPU itself. And if you want to learn more about this, you can watch your talk. And then again, we keep doing this for other applications. This is for sparse matrix vector multiplication machines. Again, bioinformatic workloads, we took alignment algorithm, and then we implement this alignment algorithm in this UpMem system, and we saw good performance benefits compared to a CPU and a GPU. Another example of a real architecture, this time around from Samsung, is called, before it was called FIMDRAM, and was announced in 2021, and was targeting machine learning algorithms, so particularly neural networks. So this is an example. This FIMDRAM architecture from Samsung uses these 3D stack memories that I mentioned before. So this is a good example for you to see that some idea that initially was proposed in academia, moving from industry years later on. So it's a similar setup. We have several layers, these layers of memory, and there is a layer that has logic, and then they implement some key functions inside the memory itself that are key for convolution inference in this case here. So this is an example of that unit that they have inside the memory itself. Is a SIMD type of processor that has a multiply and adder type of unit, because this is the key thing in inference for neural networks. So it, again, is supporting some really finite number of instructions, but was shown to perform really well for this convolution neural networks. Again, this is just a design or a layout of the chips, so you can see here across every 2 DRAM blocks they have some what they call processing center units or something like that. Inside that memory layer that I mentioned before. So this is from 2021. Samsung, sorry, keep working on this. And this year in this, there is this conference called Hot Chips, where usually people from industry goes to talk about their new development. And Samsung presents some new processing near memory solutions targeting, again, generative AI. So think ChatGPT, for example. And so if you look at ChatGPT or GTP3 and you try to profile that application, you're going to see that there are two main steps, summarization and generation. Summarization is mostly compute bound, so it can be accelerated by GPUs, for example. And generation is mostly memory bound, because a lot of the time, most of the time, is spent on moving the data from the whole CPU to the GPU memory and back and forth. So here again is a breakdown of this generation step. The main function is the generation step, is general matrix vector multiplication, GMV, and 60% of the latency for inference for this particular implementation of GTP was spent over there. And so this is a key function that you want to accelerate using processing memory. So they propose 3 different solutions for processing near memory and generative AI. The first one is this HBM pin architecture. It's just a renaming of the thing that I mentioned before, the FIMDRAM from 2021. Is the same architecture, and they Samsung pattern with AMD to add this HBM PIM device together with this AMD GPU graphics card. And then they do some experiments, and they see really large performance and energy benefits when you do the inference using this pin capable GPU system. Yeah, so it accelerates GPT by two times. They also propose a solution. So that particular solution with the GPU is more prone for the cloud setup. They also look into the case where we want to do the inference in the edge device itself. Why you might want to do inference in the edge device, because first, data center cost is really high nowadays. Also the power that it consumes in the data center is quite high. It creates privacy issues and also creates latency issues, right? If you don't have connections, for example, what do you do? So there is this case to do generative AI in edge devices themselves. And usually edge devices like phones use this what's called low power DDR models. They are DRAM DIMMs that are particularly designed to be low power. So they basically take that same concept of that CMD vector engine that I mentioned before, and instead of implementing using that 3D stack architecture, they implement it inside this low power DDR architecture. Again, here you can see that they use these PIN engines connected nearby the different DRAM banks, and the P engine are quite similar to what I mentioned before, that implement some simple units, some simple functions like multiplication and some arithmetic operations. And then again, for GTP2, they show 4 times performance and 70 times energy reduction. Take all of those numbers with a grain of salt, because usually those presentations from those memory manufacturers or presentations in this conference are more marketing related than scientific presentations, but it gives us an indication where the industry is going to. So another solution that Samsung proposed for this process near memory architectures is this other architecture with this memory expander graph interconnects that's called CXL. Basically, they have, I think I have a figure here. So basically, this CXL is basically a way of you to put a pool of memory into your server, for example, because you want to scale the size of, you want to scale the memory capacity in your system, in the server node, in the same time that you want to provide low cost. And then the industry recently came up with this standard to do that. They call CXL. And basically what Samsung is doing is taking these standards and including some PIN capabilities in that network itself, inside the controller of that network or inside the memory device that is sitting connecting that network itself. So they have these two solutions, and this is particularly interesting for training of these generative AI type of models, because training is quite a capacity-bound problem for larger language models. And again, they show that this type of system, by having the simple PIN units inside the CXL memory expander, can provide 4.5 high energy efficiency and 53 times higher throughput than having multiple GPUs. So yeah, you're going to see this more and more in the market moving forward. Again, another proposal from Samsung is this IEDM. Again, it's quite similar to what I just mentioned, is moving some computation inside the memory device itself. And this particular system was designed for recommendation systems, which is another important machine learning algorithm that people have been looking at for this type of architectures. Another solution from SK Hynix is called AIM. SK Hynix is another memory manufacturer again. They are quite, at a high level, is similar to what Samsung is proposing, including some logic around banks in the DRAM array itself. Again, this is targeting neural network inference. Alibaba also has its own architecture that uses 3D stack to integrate computation together with the DRAM die. This is more close to the Tesseract architecture that I mentioned previously, where the computation is sitting in the logic die of the 3D stack architecture. So yeah, so as you see, there is even though this process near memory so ideal or proposal is quite old, it's from the 70s. Nowadays, they are gaining a lot of traction from industry itself in different ways to accelerate key applications. So I guess this is good to motivate you guys in this direction. So it's just not us working on this. Is there any question related to the process near memory systems? Okay, so I'm going to move next to the processing using memory systems. This is a bit different from what I was mentioned before. The idea is still to do computation where the data resides, but now we are not going to include any logic elements to do that. We are going to use the properties of the memory device themselves to do the computation. And we are going to start really simple. We are going to start by allowing my memory to copy data internally without the support of the GPU of the CPU, or initialize a data location with zeros or one without the assistance of the CPU as well. This is a key application. These two operations are key for many larger applications in the system, like forking or checkpointing or page migration. So Google have shown that 5% of the cycles in Google data centers are spending this type of operations. You might think that this is a small number, but we have to think about how many servers Google have. So this is if you can cut this to zero, you gain a lot of, particularly in energy. And in the way that this is done today, so again, you have the system, you have your processor, and you have your memory, and you have a bus to communicate the two. And the way that if you want to copy a memory location to another memory location, the CPU needs to read the data. And this is, yeah, I was missing. There is a slide missing here. But basically, what needs to be done from the CPU point of view, you need to read this block from memory into the cache hierarchy, get to the CPU, then you write to the new location and move the data back to the memory itself. Even though if you want to just do a small portion of the data that will be copied, you need to go through this process, which is quite high latency because you need to read through this bus that is quite slow into the CPU through this cache hierarchy and also consumes a lot of energy. Instead, we want to do that. We just want to tell the memory, copy location A into location B, and the CPU does not interfere at all. If you can do that, this provides you low latency and low bandwidth utilization because you don't need to go through this bus. And there is no cache pollution because you're not copying any data into the cache, and there is no unweighted data movement. So you go to a baseline copy of 1,000 nanoseconds and 3.6 microjoule to 90 nanoseconds, for example, and a large reduction of energy in the systems. So before I explain how this can be done in the memory device itself, I need to give a brief background of a DRAM. Does anyone know how is the inside of the DRAM here? Okay, so we don't need to spend so much time, I guess. So this is a DRAM model, is what you're going to buy if you go to a store, and this DRAM model have several DRAM chips, and inside the DRAM chip you have several DRAM banks, and inside the DRAM bank you have several DRAM cells which are organized in what is called a subarray, which is a 2D organization of those DRAM cells. So DRAM cells are connect horizontally to what's called a word line and vertically to what's called a bit line. So bit lines, DRAM cells connecting a bit line share a sense amplifier. The sense amplifier, a collection of sense amplifiers, is what we call a row buffer. A DRAM cell itself store data using a storage capacitor. So this is a simple capacitor, and to access this capacitor, there is an access transistor that is controlled via the word line. So this is overall the structure of DRAM. So this is another view of the same structure over here. So we have several banks. The banks share some bus together, and also the chip across all of the banks share some I/O logic. Inside the bank, you have several subarrays, and inside the subarray, you have this row of DRAM cells and this row buffer. So the way that the DRAM cell operates is based on three main commands: activate, a read, and a precharge. And I'm going to really briefly talk about how this works. So before anything happens inside the DRAM, you have your cell storing some data using some voltage level, and you have your bit line set into a reference voltage, usually half of VDD. So to access some data, the memory controller sends activate commands to the DRAM location that you want to access. And what this is going to do is basically raise the word line, which is going to connect the storage capacitor to the bit line. The capacitor is going to lose charge to the bit line, creating some perturbation to the in the bit line. This sense amplifier is going to be enabled, which is going to amplify that perturbation that was put in by the storage capacitor to the bit line, either to VDD or to 0. And then the value that was amplified by this amplifier is written back into the storage capacitor, which is restoring the original cell value. So after you deactivate command is performed by the DRAM device, you can issue several read and write requests to read data that is latched inside these sense amplifiers as needed by the processor. Once this is done and you want to access another row, you need to issue a precharge command, which basically is going to disconnect the storage capacitor to the sense amplifier. You're going to need to put the bit line back to the reference voltage for the next access, so back to VDD over 2, and then finally you disable the amplifier. So you are now ready for accessing another row. So again, we want to be able to copy one row to another row inside the memory device, inside the RAM, without the interference of the CPU. So the way that we are going to do is, again, it's another view of inside the DRAM subarray. We have several of those DRAM cells connected together. So in this example, 4 kilobytes of them. And what we're going to do is, first, we're going to access a row. We're going to send activates to a given row. This activate is going to transfer the row to the row buffer. This is exactly what I just explained before. And next, we are going to access the destination row. And before, instead of sending a precharge and then sending activates to the destination row, I'm not going to send a precharge at all. I'm just going to send the activate to the destination row. Since the data from the first activate is latched here in this row buffer, what is going to actually happen is that the data that is latched here is going to be copied back into the destination row, and this row B here in DRAM. So basically what we achieve was an in-DRAM row copy without the intervention of the CPU at all. You don't need to move these data blocks to the DRAM. You basically, by manipulating the way that DRAM is accessed by these activating precharge commands, and the way that this row buffer and amplifier it works, you can do computation inside the memory device natively. So you don't need to include any hardware to do this extra computation itself. So the key idea here is to issue two consecutive activates to the source and destination locations inside the DRAM array, which have no hardware cost at all to do so. So this is another view of what is being done at the cell level. So we have the source row, we have the destination row. Initially, the source row has some voltage level which is high. The destination row has some voltage level which is low. And then you have your bit line, you have your sense amplifier here, and a collection of sense amplifiers row buffer. Initially, this bit line is set to VDD over 2. So you send the first activate to the source row. The data is going to, the cell is going to be propagated to the bit line. There is some perturbation in the bit line. This amplifier amplifies that difference. And then you have the data being putting back to its original cell level. In this case here, VDD. So if I want to do a regular access to the destination row, next I would send a pre-charge to put this bit line back to VDD over 2, but I'm not going to do that. I'm just going to simply send activate to the destination row, and since this is amplifier here, the voltage level is higher than the voltage level here inside the capacitor, the data is going to be copied to the destination row itself, enabling us to do this in DRAM row copy. So in this paper, we show that by doing so, we can significantly reduce latency and reduce energy in a system because we don't intervene. The CPU does not need to intervene at all. And this is what we call row clone. And you can ask, like, can you do this in regular DRAM devices? That there were another research group that took this idea of row clone. They bought DRAM DIMMs, off-the-shelf DRAM DIMMs, and they showed that we can do these row copy operations in regular DRAM DIMMs by violating DRAM time parameters itself. So it's actually possible to do what I just mentioned in regular DRAM chips. Of course, there are some error involved with that, but anyway. Yeah, so we also put up some infrastructure to enable testing and end-to-end design of these processing using memory solutions, particularly this row clone and TRNG for random number generation. With this framework that's called PyDRAM, is basically we have this FPGA board, and this needs to be done in FPGA board because we need to be able to manipulate the memory controller with different timing parameters to access the DRAM array itself. So we need to implement our own memory controller. And in the system here, we enable some end-to-end encapsulation of these processing using memory primitives to accelerate some applications. This is open source, and we show that it can, using this framework, we can do this row copy and initialization and improve throughput compared to the overall system. So if you are interested, you can check the paper and also the presentation. So there are several improvements on top of row clone itself. And several follow-ups, so you can do copy across subarrays using Lisa, across different granularities in the bank using Figaro, across banks using this non-paper, and also using other do more primitives like AND, OR, and NOT operations. So this is one example of them. So if you want to move the data inside one subarray, is exactly what I mentioned. But if you want to move data across the different subarrays, you are limited by the low connectivity of the DRAM device itself. So our goal is to basically mitigate that problem. So what we do, basically, we connect the different subarrays in a single DRAM bank using isolation transistors. And by doing so, we can enable this bulk data copy across the different subarrays in the same chip. And this enables other applications and gives other performance benefits other than just the data copying. This is what we call Lisa. There was this Figaro that also enables moving data at different granularities inside the DRAM array, so it's not necessarily at the granularity of a row, and NOM is for interconnects. So other things that we can do using processing using memory is supporting Boolean operations like AND, OR, NOT, and MEG. We want to do that at low cost by using the analog principles of the DRAM array itself to perform the computation. We have proposed this architecture called Ambit that does so. I'm going to explain it next. And by doing what Ambit proposed, we can get 30 to 6 performance and energy improvement in a regular architecture. And other memory technologies can also do that using, for example, RowHammer or more non-volatile memory. So this is the key idea of Ambit. So before in row clone, I was accessing 2 rows simultaneously, right, to do the copy. And now, instead of accessing 2, I'm going to access 3 rows at the same time. So you have row A, B, C, and then each one of them have a cell with some voltage level stored there, right? So I'm going to send activate to all of the 3 rows at the same time. They are going to perturbate the bit line. This perturbation of the bit line is going to be amplified into the majority of the voltage levels that was initially stored in the tree. So the majority of the 2 here is actually a high voltage level, right? And this works like this because of the way this is a differential sense amplifier and the way that this is actually working. But the important thing here is that in the end, when you in the end of this triple row activation, the final stage that you have is basically a combination of AND and OR operations of the 3 rows that you access. And by having a control row over here, you can perform either OR operations or AND operations of the other 2 rows. So this is the semantics of it. So basically you copy the data into some dedicated rows because this operation is destructive. Then you send the activation to the 3 rows at the same time, and then you copy the result back to another row. And this is was initially proposed in this call paper in 15, and later on we improve it in the ambit paper. So we can do AND and OR, we can do copy. The thing that we are missing to be Boolean complete now, function complete, is not operation, right? And the way that we propose to do not operations and then be functional complete is by using the design of the simplifier itself to get a negated value of the data. So again, this is the design of the simplifier. Is it simply two back-to-back, two NOT gates connected back-to-back? And since these are NOT gates, one side of the bit line stores the regular value and the other side of the bit line stores the negated value. So what is being done here to enable NOT then is basically redirect the value that is stored in the other side of the bit line bar here, back to the DRAM self using this other word line over here. So with that now, we have NOT operations, and then we are function complete, right? We can do NOT and OR, NAND, NOR, sorry, XOR and XNOR. And we compare this approach of processing using DRAM in the ambit case with a CPU, a GPU, and a 3-stack memory, and you see that we can have much larger throughputs than those systems and really large energy savings to those systems. So we use these book bitwise operations to accelerate several key applications, which we use them. For example, by database operations, use a lot of masking, for example. DNA sequence also uses bitwise operations, encryption algorithms, and we saw when you do this computation, these algorithms, following what is proposed over here, this triple row activation, you can significantly improve performance compared to a baseline CPU. This is the ambit paper. And then on top of that, so we can do AND or NOT. We are functional complete, but how you design arithmetic operations, right? How you can combine this AND or NOT operations to do addition, multiplication, or subtraction. So this is actually one of the readings that's going to be was assigned for you guys during the semester. So I'm not going to talk much about it. So, but is this SimDRAM proposal? Basically, we propose a way of generalize given computation into the sequence of DRAM commands that implements a given operation. Like, for example, this is addition. So by combining AND or and NOT addition gates together, we can do a full adder inside the DRAM itself. So it's a 3-step methodology. Here, I'm going to briefly talk about the first, about the 3 of them. So the first step here, basically, we want to convert the AND or representation of our algorithm into a majority representation because it's more efficient to do computation. And this is done using some heuristics. And then the second step, this is the first step. The second step takes this NOT implementation of your key operation and generates the sequence of DRAM activate and precharge commands that implements the target application that you want to do. And this is broken down into 2 tasks: allocating the DRAM rows for computation and then finally generate this microprogram. And finally, we designed some memory controller that can orchestrate this computation transparently from the programmer itself. So I'm not going to talk much about it because again, is one of the seminar talks that we are going to have during the semester. This paper addressed several system considerations to enable this processing using a memory system, and then we evaluate it against CPU, GPUs, and then we see great performance in terms of throughput, energy, and performance. And this is the SimDRAM paper. There are several follow-ups that we are currently studying for SimDRAM, for this processing using DRAM type of solutions. For example, how can we do computation with different granularities? We are going to see over there that we need to do some data layout conversions to enable shifting efficiently, but this creates some cost. So how can you do that computation without that? So we are constantly working on improving the substrates one step at a time. So there are other operations that can be done using the similar mechanism. One of these examples are physical unclonable functions. So you feel free to leave if you have. So I still have some couple of slides to go through, but if you can feel free to leave. So those ones that can stay, I shouldn't take much time. It's just to give example of the continuing another example of other processing using memory architecture solutions for physical unclonable functions through random generation, system support for true random generation. So basically the scope of the range of operations that can be performed using processing, using memory, following the same type of behavior that I mentioned for row clone, ambit, and SimDRAM can be extended for many other type of applications. Another example is of processing using DRAM that is a bit different. What I just mentioned is using lookup tables. So the problem with this, all of this work that I just mentioned is that, okay, they can enable data movement, bit shifting, bitwise operations, and arithmetic operations, but there are some computations that you cannot compose using those operations, like transcendental functions. For example, sine, cosine type of applications. And the goal of this work here is to extend further the range of operations that you can do using processing using DRAM. So the key idea here is instead of using computation in the more common way, using some ALU to do computation or some transformation to do computation, we are going to memorize the results of the computation in some lookup tables, and then store these lookup tables inside DRAM itself. And by replacing this computation with this lookup table lookup, we can generalize the processing using DRAM computation to other operations in this lookup table operations. So I'm not going to go into details on how this is done over here, but basically we store this is the DRAM array that I just mentioned before, and you keep the lookup table with the pre-computed results inside the array, and then we change the DRAM array itself to have some matching logic to match the query that you want to compute for computation, and then some access transistors to filter out or to store the results that match the query that you are trying to copy or try to carry from DRAM itself. So this gives us a lot of larger throughput in the system. Yeah, so for example, here we check basically the row index that you're trying to accessing to the matching logic and the query that you want to have, and then you go one by one until you have a match. So here in this case, the row that you are accessing matches the input vector that with the query that you want to compute, and that data is copied to the output vector. And this repeats for each one of the designs. So in this paper, we evaluate 3 different architectures with different performance, energy, and area trade-offs, and we evaluate and we show that our designs cover a broad design space across this trade-offs architecture here. In the paper, you also talk about system integration, how you can go from a C application into this execution in the DRAM substrate itself, which I'm not going to mention here. Again, we evaluated compared to a CPU, a GPU, and this process near memory architectures, and we show high performance improvements, high performance per area improvement, and also high energy savings compared to these architectures. So yeah, there is the talk, and this is what I have to cover for processing near memory and processing near memory. Really briefly, I'm going to talk about how to enable the adoption of processing in memory overall. So as I mentioned earlier in the talk, for you to enable processing near memory, we need to rethink several components of the system, from the application, how to do programmability, how to enable system and security, how to compile coding for this, and how to enable infrastructures that enable you to test this type of systems. And all of this comes with a change of mindset. So you need to move from this processor-centric mindset to this memory-centric mindset. And we can go there one step at a time instead of trying to change everything at once. There are many works in this direction on, for example, how you do the bare minimal change so you can enable computation, how you can ease programmability for systems like that UpMem system that I mentioned, those two works over here, how you can keep cache coherence, so how you can keep the memory and your processor coherence, having the same view of the data without incurring too much overhead. So there's also solutions for that. How you enable synchronization across the computation that are executed inside your memory devices, how you enable virtual memory for this processing using memory architectures and processing near memory architectures, how you could do code and data mapping, and there are many other works on this system integration topics over here. I'm going to briefly mention on how to identify workloads that can be good candidates for this processing memory architecture over here, right? So if you have a workload and you want to figure out if it's would be beneficial to execute it using this processing in-memory architecture or not, you need to have some indications from some properties of the application itself, right? So to do that and tell you this new application could benefit for ping or not, we create this the move methodology that basically takes your application, runs into some three-step framework, collects some metrics from this application to characterize it, and later on decide if this application could benefit for processing memory or not. I'm not going to get into details of this again, because it's another reading that is another seminar that we are going to have during the semester. But basically, the first step of this move methodology is to understand, do some filtering of your applications by collecting some hardware profiling metrics of the application. Then in the second step, you collect some properties of the inherent properties of the application itself, about the locality that the data access of the application have, so both spatial and temporal locality. And later on, you classify the system that the application is running with three key metrics, and run some simulations, and based on that you classify your application into some different classes of data movement bottlenecks, and each class of data movement bottleneck has some correlation with the processing memory architecture that we are going to use. This is the move infrastructure, and again it's open source, and you can get over Zoom, over GitHub, and there is the talk for it. And if you are assigned to this paper, please reuse the slides, because it will be much easier to go through it. So to conclude, to enable processing memory, we need to so to enable fundamentally energy efficient systems, you need to be data centric. We need to think about data centric architectures, and also to enable high performance architectures, we need to think about data centric architectures. And the overall goal here is to compute with minimal data movement, encourage minimum data movement in your system. And all of that require us to think about intelligent systems that are data-driven, data-aware, and data-centric. By doing processing inside the memory, we can have large orders of magnitudes performance and energy improvements for new applications and new computing platforms, which allows us to do much more, right? Because if you have a larger, faster, and more efficient computing, this fundamentally in the end lets you to further understand of the environment that you are surrounding with. And then the future for processing memory is just starting, especially with this new push for industry, but not only because of that, because we are having this demand from applications and for these limitations that processing-centric systems are facing more and more over time. Again, this requires us to revisit the entire system stack, but we can go there step by step. So to conclude, I guess the main thing here is that we are designers, we need to be open-minded to what is next and not only think about the type of system that we are designing if you want to have better systems in the future. Again, if you want to look at more about all of those books that I mentioned here, you can look at this book chapter. We also have several videos in our website with some classes on processing memory. This is the class on 2022. We have also a focus class only on that, and we are going to keep giving some tutorials in key computer architecture conference about this particular one here is about this real processing memory systems and accelerating PIM in different ways. So we have an upcoming tutorial on PIM on this microarchitectural conference in October in Toronto, and all of the resources that I mentioned here are available online. You can check our GitHub, and that is the end of the talk. Sorry, I speed up a little bit in the end, but I'll be glad to take any question, if any. Okay, thank you so much.